In this video, we're going to be talking about the properties of waves. A wave is basically a disturbance that propagates. Propagate means spread. So it's a disturbance that transmits energy from one location to another. Now the thing with waves is that they don't carry matter. Only energy can be transferred. Now there are two different types of waves: mechanical waves and electromagnetic waves. Mechanical waves require a medium to pass through. Some examples are longitudinal waves and transverse waves. Meanwhile, electromagnetic waves do not require a medium to pass through. And electromagnetic can already tell you that all of these parts in the electromagnetic spectrum, these parts in the electromagnetic spectrum do not require to pass through a medium. So for example, light, it can pass through a vacuum, like it can pass through space, because space, it doesn't have a medium, it's a vacuum. So because of that, we can tell that light is an electromagnetic wave. Now, when we look at a wave, there are multiple properties to it. So I'm going to draw the wave. So there are these two parts over here. The vertical line over here is the displacement. And this horizontal line over here is the distance. However, it can also be the time in some situations. Now, this wave, I'm just going to draw a wave. This is an example wave over here. The top part is the crest. The bottom part is the trough. And the distance between this horizontal line and the trough, or the distance between the horizontal line and the crest, is called the amplitude. This is also the amplitude. And the distance between this crest and this crest, or the difference between this trough and this trough, is called the wavelength. Then what we have over here is at this point where it all starts, it's called the origin. We typically use O, but I'm gonna write it out. And there's also one last part. It's called a time period. We can take whatever point, and as long as it matches, as long as the wavelength of that point matches up to the same elevation and the same distance, those 2 points are basically symmetrical. So these dots would represent the time period. Some important parts of a wave is called, one of them is called oscillation. Oscillation is the periodic movement or the periodic motion of that wave. So the wave is going like this, and it's going and going and going until the source over here is disrupted. If the source is disrupted, then what happens is it basically is a chain reaction. It's like dominoes. Although this part is gone, this part is still going. If this part is still gone, this part is still going. However, it won't go forever. It'll eventually stop. And that's kind of how light moves. If a star goes through a supernova, and completely explodes, then all that light is released. However, the thing is that because of the distance and like how far the star is, sometimes when we look at the night sky, we can see stars that used to exist, but because light is taking a very long time to reach our eyes, although the light is coming to Earth, the star could have already been like a black hole or something like that. Or it could have died, basically even though the star is emitting zero light, since the light wave is still traveling, what's happening is that it's still showing up. But eventually what happens is, since the source is now removed, everything else is eventually going to get removed. So oscillation is basically the periodic movement of a wavelength. And since that wavelength is repeating forever until the source is disrupted. Now, there are separate parts when it comes to a wavelength and the amplitude. I'm first going to start with the wavelength. So when the wavelength is very symmetrical, like this, it's a transverse wave. The wavelength is typically shown like this. Wavelength is typically shown in this symbol. Now, sometimes, however, this is a transverse wave. However, a longitudinal wave doesn't exactly have that kind of equal balance between the waves. Sometimes this could happen. We can experience what we can experience is we can have compression in this area. But it can be spaced out in this area. So longitudinal waves act like that. Next, there's frequency. frequency is measured in hertz. And the thing about frequency is that if we look at the wavelength, if the wavelength is very long, we can tell it has a low pitch because it is much more stable. However, if the frequency is high, like it has a shorter wavelength, then it has a high pitch. And we can also tell the difference with amplitude. So amplitude is like this. And the thing about amplitude is that if it's a pretty low amplitude, then it's broad or it's soft. If the amplitude is like broad, pretty like nicely spaced out, then it has a soft amplitude. But if it's not spaced out and if it's very narrow, then it's it's loud. So this here would have a high amplitude. And a high amplitude means high energy, but this part over here has a low amplitude because the wavelength is very broad. So it has a low amplitude, or in other words, low energy. And then lastly, we have speed. For the wave speed, it's actually kind of easy to understand, and I'll explain it. So we know that speed equals distance over time. If speed equals distance over time, it says over here, wave speed equals frequency times wavelength. I'm gonna start with the wavelength first. So wavelength is basically nothing but the distance between one crest to the other crest, or the difference between one trough to the other trough. So the wavelength is basically nothing but the distance over here and the distance per cycle. And the cycle, like, it's happening over here. This is one cycle right here, the one I just highlighted. And it's the distance between those two cycles. And we're going to multiply that by the frequency. Now, when we look at the frequency, we see that the frequency with the much more broader wavelength has a low pitch compared to the one with a narrow wavelength, which has a high pitch. So I'm going to draw two examples over here. This one's going to have the low pitch or the broad wavelength, and this one's going to have the high pitch or the narrow wavelength. So, alright, so there's the one with the low pitch, and then I'm going to draw the one with the high pitch. So, when we look at this horizontal line that's crossing, we can see that for the low pitch, it's crossing this point less times than for the high pitch, because this is crossing it more times. We can see that over here because it's crossing this horizontal line here more than this over here. So we're seeing that frequency is having, so we can see here there are more cycles per time than over here. So we put cycles over time. And if we know our math, cycles cancel out, and would you look at that? Distance over time. So we said speed equals wavelength, which is distance, and times frequency, which is the cycle, or because we crossed the cycle, it turns to 1 over time. So that's actually kind of how you explain it. And if we were to look at this, it would basically just be the speed is equal to wavelength times frequency, which is just nothing but distance over time. And we can see this formula matches this formula, proving that wavelength times the frequency equals the speed. So this is all about the properties of waves, and we also got a pretty nice demonstration and introduction to some wave formulas. We'll be getting more into this later on, and also we'll be understanding much more higher and in-depth properties of waves and what happens to waves in certain situations.